Here we go. Today we're going to talk about wiring a model railroad for analog or DCC. They're similar, and so I'll talk about both of them. Well, there we go. There's several things that are important for good wiring, and that's making sure that your track has tight rail joiners. You also need to provide expansion joints, and you need to make sure your track is secured with glue. I have got several things in here about track laying that I'm going to skip over since we're in kind of late in the day. Good track laying is important for good wiring, but we'll talk about those at a later date. Loose rail joiners can cause kinks, obviously, as you can see in these pictures. Good rail joiners like Picos are tight, and they keep the track from tinking. Do not crimp rail joiners with pliers. They just give up. I'm not going to read through all this, but the importance of this particular screen is to remind you to make sure you leave expansion joints. A lot of people will solder rail joiners. That's okay, but if you do, make sure that you cut expansion joints in your track. Here's an example of cutting an expansion joint. Secure track to the road bed using glue. Well, the reason I prefer glue to nails is that nails can cause depressions in the track, where if you use glue, you just lay over depressions or bumps, which smooths the track out. Now we're getting to wiring. The differences between DC and DCC, the wiring is very similar for both systems. Something I'm going to talk about in a minute is something called common rail wiring, which we're trying to get away from. I also mentioned why I always use stranded wire and why I always twist my wire pairs. Both DC and DCC systems should be wired in blocks. Conversion from one system to the other is easy if you do that and you don't use common rail, which I'll describe in a minute. Common rail. It used to be that electrical parts were fairly expensive, and to keep costs low, they would only switch one of the two rails, only isolate one of the two rails. You'd have one rail which would be called the common rail, and all of your in the DC systems, when you use several power supplies with several throttles, one rail would be common. In other words, it would not be isolated from block to block. The other rail would be isolated and would be connected to the positive side of the power supplies and would be called the hot rail. Common rail should not be used in today's layouts, even if you're running with just DC, for the reasons that it's hard to convert to DCC later on. I like to use stranded wire. Number one, it's less likely to be damaged when you strip it. Often when you strip solid wire, you can cut score the edge of the wire and it'll snap off later on. Stranded wire is more easily to bend in the larger gauges. Stranded wire is easier to splice, especially with suitcase connectors. Now, suitcase connectors can work with stranded or solid wire, and that's kind of quite frankly, a false statement. But suitcase connectors do go on stranded wire easier. If you're using DCC, stranded wire will carry the high frequency digital commands with much less signal loss than solid wire. And when I say high frequency, it's really kind of mid frequency, but you still have less signal loss on stranded wire. I always twist my wire pairs, mainly just for neatness and also to prevent electromagnetic interference between different circuits. If you run a pair of wires over for one circuit over a pair of wires for another circuit, you can sometimes have interference between the two. If they're twisted, you'll never have that. And it's cheap to do. I use an electric drill as shown here in this picture, and quickly twist the wire pairs. Again, it makes everything much neater. I'll take a minute here to explain some of the basics about electricity so that you'll better understand what I'm going to tell you in a few minutes. Electricity is measured or described in three different ways: volts, amps, and ohms. And if you understand those three things, it's easier to understand electricity. Also, I'll talk about why I don't depend on track to distribute power to the layout. Volts is the pressure behind electricity. Amperage is the amount of electricity. If you think about water, voltage is the pressure behind the water. Amperage is the amount of water coming out the hose. And ohms is the resistance to the flow of electricity. If you crimp the hose, you're causing resistance to the water. Rail joiners can cause high resistance to a current flow and therefore voltage drops. You'll lose pressure when you depend on rail joiners to pass current from one section of track to the other. Code 83 nickel silver rail can lose as much as 1.5 volts and 12 feet at 3 amps. 3 amps is how much current consists of 3 HO engines, sound HO engines would draw. In 12 feet, you can lose 1.5 volts. You've got usually 14 volts in a HO system. So 1.5 volts is almost 10%. Loss of voltage will cause locomotives to lose power and therefore slow down. Wiring the layout is what this clinic's all about. So I'm going to spend a little bit more time talking about that. I prefer bus wiring, and a bus is a backbone of power or wiring that is run around the layout and connected to the track through what we'll call drops. A bus is going to be a much higher gauge wire than the drops, and we'll talk about what size that should be and why in a minute. And there's a couple ways to connect your drops to the bus. We'll talk about that as well. Another thing that's important to do is document your wiring plan, and this is a good time to talk about that. I like to take the layout plan, the actual track layout, try to draw it in as large a scale as possible, and then decide where the bus is going to be. If I'm going to have multiple buses, I'll make a chart of which color pairs I'll use for each group or each bus and its drops. I make a drawing of this wiring for more clarification later on if I need to go back in and repair things, or if somebody else needs to go back in and repair it, and they'll know what I did. Buses should be run as short as possible to minimize voltage drop. Even though we have a large drop in track, we still have a small voltage drop in buses. A single bus can go in more than one direction. In other words, you can have a bus that's going from one or going around a loop of track and then break off a second bus to a yard or something like that. If If a block is close to a power source, it may be simpler to start at one end and run to the other. We're talking about power blocks here, and I can't remember what I was thinking when I wrote that, so I'll ignore it. After you design your layout and decide where the electrical blocks should be, electrical blocks we haven't really talked about yet, so let me take a minute to explain that. In DC, electrical blocks are used for every train running will have its own throttle, and each train will be in a separate electrical block that throttle will control. In DCC, it's totally different. In DCC, a throttle can control a train in any block regardless. Blocks are used for power control, so that if you have a short in one block, it won't shut down the whole railroad. There's also something called signal blocks, which I'm not going to get into in this particular clinic, because it can get, it's quite a bit more involved. So after you design your layout and decide where the electrical blocks will be, that plus where the drops are located will tell you how the buses need to be run. So if you have multiple blocks, you're going to have multiple buses, and each bus will be run from a location of wherever your electrical equipment is to each of those blocks. A bus is a pair of wires that distribute power to the track. We've pretty much covered that. The number of buses your railroad needs is dependent on the design of your layout, which is the number of blocks you're going to have. And typically, a small layout will be divided up into maybe 4 blocks. If you have 2 tracks running around in a, let's say, an oval, an inside and an outside track, each of those would be a block. If you have a yard, that would be a block. And possibly if you have a lot of sidings, they could be part of a 4th block. You'll need to run a separate bus to each one of those electrical blocks. I probably should have had this slide before I had the previous slide. What size of wire should you use? Every kind of wire has resistance. The thinner of wire is, the more resistance per foot it will have. We need to choose a wire size that will allow the current we need to pass through the wires without causing too much voltage drop. The simple rule is the bigger the better, but then obviously you don't want to get too big. Larger diameter wire costs more, and there's no reason to spend more money than is necessary. This chart shows you the amount of voltage drop that you have using per foot using a particular gauge wire at a certain amount of current. Again, let's take 3 amps, which is in the middle of the chart, which would represent a lash-up of 2 or 3 sound locomotives. 14 gauge wire is going to give you 1/1600ths of a volt drop, which is very reasonable. The last part of the chart shows you the amount of resistance, which is much at a certain frequency, and that's less important. Has more to do with DCC and is a little bit more complicated to cover in this clinic. Let's concentrate on the voltage drop. 16 gauge wire is going to drop more than twice as much as 14 gauge wire. Obviously, there's a mistake about 18 gauge wire. I probably have 16 and 18 gauge reversed. And 20 gauge wire is even more. Again, we're looking at HO 3 amps. That would be the most current you'd want you'd have at any particular time. N scale would probably be more in the 1 amp to half amp range. On most HO layouts, using 14 gauge buses and 18 gauge or 20 gauge drops. That way you're going to have the minimum voltage loss without getting up into the 12 and 10 gauge wire, which you only use on really big layouts. Most N-scale layouts are going to use 16 gauge buses with 20 to 22 gauge wires. And always use stranded wire, always twist wires. Again, those are personal preferences. The best way to find out what gauge wire you have, if in fact you don't know, is to look at it. Just about any wire you buy is going to be, the gauge is going to be printed on the wire. This is 18 gauge wire, as you can see. First the brand name, then 18 AWG, which stands for gauge, and then another brand name and some more information about temperature, and beyond would be voltage. How many drops should you install? Well, most of us use flex track, and flex track being 3 feet long, I normally use a drop every 3 feet. In other words, between every pair of rail joiners, I use a drop. Now, that's not always the case. If I have a short piece of track, I might solder the rail joiners to the longer piece of track. On a simple oval of track that's 24 feet long, there should be about 8 drops. A layout with a double main would have twice as many drops. And if you had 2 blocks, you'd have each of those set of drops connected to different buses. Each siding will have its own drop, maybe 2 if they're longer than 3 feet. Yards will have a drop or 2 on each track. And turnouts present the opportunity for a lot more drops. People ask me what to do in the case of turnouts. Typically, I will solder the throat of the turnout to the track that is attached to it. That will give the turnout all the power it needs without any voltage drop due to rail joiners becoming loose. On the other end of the turnout, I normally don't solder, but I'll make sure that the track immediately beyond the turnout has a drop on both sides. Drill a hole as close as possible to the outside of the rail where the drop is to be installed. Installing drops. You can see where the drill bit is. I just drill a hole down through the cork, the table, and everything else. I then take a piece of wire and put a little hook on it. I clean the rail where the drop is to be connected with a wire brush or scrape it with a knife. If it's new rail, I may not have to do either. I attach the wire at the base. I think you can see here the bent wire being where it's soldered to the track. It's kind of messy looking because of the flux, and I'll explain that in a minute. 2 ways to connect drops to the bus. A T connection needs to be made between the drop and the bus wires. You need to connect the drop to the bus either with suitcase connectors, and if you're not familiar with those, I should have included a picture, but I didn't. You could also solder the drops to the bus if you want to save money. It's a lot more time consuming and back breaking because you're under the layout, but it is a way to do it. And some people say the best way to do it. I'm satisfied with suitcase connectors, but if I had the time and the energy, I would solder. Here's suitcase connectors. There's 3 different colors there because there's 3 different sizes. It's important that you have suitcase connectors for bus and drop designed for two different size wires. If you can see this brown suitcase connector on the bottom, you'll see one slot in this metal piece that's circled with the red circle is wider than the other slot. That is so that the larger bus wire, which goes through the larger hole below the larger slot, and the drop wire, which goes through the smaller hole, each are tightly held without cutting through the wire. The yellow suitcase connector above it, as you can see, both slots are of equal size, and that's for two wires that are of equal size. You slip the suitcase connector onto the bus wire as shown here. Then you insert the drop wire. And in this case, I used a different color just to make it obvious. Normally, you'd use the same color. Insert it in the hole until you can see the end of it through the little window on the right. Then you take a pair of pliers and you crimp down the metal piece down into the wires until it's flush with the suitcase connector. And you can see the end of the red wire there that looks like it's been murdered. And when you're done, you close up the connector and you have a complete drop connected to a bus connection. Another way to do your bus is to do your drop connections is to solder. You should strip a piece of insulation off the bus, the green wire. That's not easy to do. I use a wire stripper on each end, and then I use a knife to cut the remaining plastic off. And you should strip a fairly long connection, a fairly long piece on your drop wire, the white wire below. Then start twisting the white wire around the bus wire. Get it twisted all the way around. Then solder it. I'm using a high-powered soldering gun there, more for the picture than anything else. You need to use a big Weller soldering iron. You can use your smaller soldering pencil if that's all you've got. The big Weller iron makes it go fast. Once it's soldered, you can't really see it's soldered there, but it is. Then you need to insulate it. I use liquid tape. It's a liquid rubber. It comes in a can and the top has a brush on it. And you just brush it on and you have an insulated connection. You can also use electrical tape, which is going to come off after a couple of years. I'll talk a little bit about creating electrical blocks, cutting and insulating gaps and blocks for DC control and DCC isolation of signals. Because each block is electrically isolated from the other blocks, there are certain things that need to be done to the track. In the case of turnouts, it is standard practice to use isolated rail joiners to isolate the frog rails from the adjoining track. The frog rails on a turnout, depending on the turnout, can change polarity. And because of that, it's important to isolate them from the adjoining track. Frog rails are the two inside rails on a turnout. You've got to isolate those from having a short on a lot of different turnouts. In other areas, it'll be necessary to cut rail gaps in order to electrically isolate rails from each of the block boundaries. In the picture here, you see I've got two soldered rail joiners. The solder being on the outside of the rail, not on the inside. You want the inside to stay clean because of the flanges of the wheel sets don't need to meet any solder blobs. One way I like to isolate blocks is I'll cut the rail as if I'm making a expansion joint. Then I'll glue in a piece of plastic. I don't know if you can see it there, but there's a white piece of plastic that I've glued in using Zap-A-Gap. I guess that's the piece of plastic. I'll put a little glue on a piece of paper and dip the plastic in the glue and place it into the gap in the rail. Once it's dry, what I'm spraying on there is Zap Kicker, which will cause the glue to set immediately. Once dry, then I'll take a knife and carve the plastic in so that it matches the format of the rail. And when I'm all done, it should be pretty perfect. Takes a little time, but you have a perfectly insulated joint. And more importantly, you have a joint that's not going to have something fall in there, a piece of metal or something get in there and short out the layout. Now, I've only done one in this drawing. I normally will do both sides, almost always do both sides, unless I'm doing it for signaling.
John?
Yes.
Did you glue that piece of plastic to both rails?
Yeah, probably.
So it's not an expansion at that point?
No, it's not necessarily an expansion joint, but I would imagine if it tried to expand, it would probably break the glue joint. Smart, it would probably be smart to just glue it to one rail if you can be that precise with your glue. You've got a good point, Randy. Okay. Blocks are used to isolate sections of track for either cab control on DC, and a cab control is where each person has their own throttle that's controlling their own transformer that is connected to block after block after block as their train progresses throughout the layout. In DCC, blocks are used so that if a derailment occurs in one block, it won't stop the entire layout. And for distributing the power so that a maximum number of locomotives can run. Typically with DCC, you've got a 5 or an 8 amp limit. I know a lot of people that will have 6 or 7 locomotives just in the yard. And if those are sound locomotives, they're drawing 1 amp each. They might have another 3 or 4 or 5 or 6 sound locomotives on the layout itself, each drawing about 1 amp. The reason that we use blocks is so that we can power those blocks in such a way that the amount of amperage available is distributed around the layout so that you don't have a situation where you've got too many engines or too many locomotives drawing too much power and causing the system to shut down. That's about as far as I'll get into it at this point. If anybody's interested, I can give them a lot more information. In both analog and DC layout, blocks are indispensable when troubleshooting problems. And this is very true, especially in a large layout. if you have a short and you don't have any idea where that short is, with blocks, you can eliminate one block at a time until the short goes away, and then you know the short must be in that block. Now with DCC, you're going to have equipment that's going to automatically show you, in most cases, which block the short is in. And the same is probably true with DC, because if you have cab control, you can quickly identify which block the short is in. Shorts are unusual, but they do happen. Turnouts tend to cause shorts sometimes, and occasionally a car will derail and you don't really realize it's derailed, and it may be sitting on a siding or something like that. And again, as I mentioned, signaling is necessary. It requires blocks. Give you some soldering tricks that I know about, and specialty tools that make the job easier. Solder should be, some people will say don't use lead. I use a 60-40 solder, 60% tin, 40% lead alloy. 60-40 solder is a lot easier to work with than the leadless solder. And the solder should have a rosin core, not acid core. Plumbing solder does not work on railroads or electronics. It'll cause corrosion, which you do not want. Rosin flux can also be purchased in a tube or a tin. I use a liquid rosin flux. This is happens to be a tube of a paste. Either way, it doesn't matter. When soldering, it's important that a strong gas-tight chemical bond be obtained. Solder is not glue. You're not gluing something together with solder. You're actually combining the molecules of the solder with the molecules of the track or the wire that you're soldering to. In order for this to happen, the material that is being soldered must reach a temperature hot enough to melt the solder. And this is achieved by always heating the metal object with a soldering iron and letting the heated metal melt the solder. I'll explain that a little bit more in a minute. When soldering rail joints, always use flux, extra flux. Put a small amount of flux on the outside of the rail before installing the rail joiner. This way, the flux will be in the best position to help pull solder in between the joiner and the rail. In other words, before you put the rail joiner on, put a little flux on the rail where the joiner is going to go. Then put the rail joiner on. Then take your soldering iron and place it on the rail joiner and against the rail, as shown in this picture here. Once it's hot, you'll see the flux starting to bubble a little bit. Take the solder and attach it to the rail joiner, not the soldering iron. Now, sometimes solder is a little difficult to get it to start melting. And what I'll do is touch it to the iron for just a second or half a second, and then move it to the rail joiner. I'll let the solder be sucked in between the rail joiner and the track and the rail. What you're looking at is a properly soldered rail joiner. If you notice, there's not a lot of solder on top. That brownish yellowish is the flux, which you can brush away. Now I've only soldered one half of this. Now I've got to go back and solder the other half. Also, notice the solder is on the outside only of the rail joiner. Here's some pictures of not so good soldering. not hot enough on top, where you get these little round blobs. Again, not hot enough. You got one big blob. Somebody melted the solder on the soldering iron and didn't wait for the rail joiner to get hot enough. The third one down could pass, but it's just a little bit too much excess solder. And the fourth one down is way too much solder. But the third one and the fourth one do show the right kind of contours. If you notice on the first two, it's bubbles. On the second two, you'll see the solder has an edge that goes into the rail, which makes it, which indicates that it has been hot enough. When I'm tinning a piece of wire, which is necessary for soldering it to the track, which I'll show in a minute. First, I take the solder, the wire. I put the wire in the iron, solder against the wire. Again, you might have to touch the soldering iron with it for a second and then draw it back down to the wire. You want the wire to melt the solder. That's a properly tinned piece of wire. Cut it off a little bit, bend it, clean the track if necessary, put a little flux on the track, solder a spot on the track where the wire is going to go, tin it. Tin means to apply solder. Once you have the track tinned where you see it and the wire tinned, then put the wire against the track and heat it up and let the two melt together. You'll get the best possible solder joints if you follow that procedure. Doesn't look like much, but I always give solder joints a pull test. Once I've soldered them, I jerk on the wire and make sure it doesn't pull off. If it does, then I do it again. There's something called resistance soldering, which if you have the money to buy the equipment, it's the best way to solder wires to track. There is a plier that each end has an electrode, or each side has an electrode, and those two electrodes are connected to either side of the power that is the power supply that is providing the current to do the soldering. You see here that I have the electrode, one on top of the track and one underneath the wire. Now I'm soldering the wire to the bottom of the track. Once I get it held in that position, there's a foot switch that I press that will then power the electrodes up, which will make them hot. I have already tinned both the wire and the track, and I get a good solder joint. It's not something that's necessary to have, but it does make things a little easier. And you can solder to the bottom of the track much easier than you can otherwise. It's important to keep everything neat. It's important to keep the wiring under the layout neat. It's easier to find trouble spots if the wire is fastened under the table in an orderly manner. Twist all your wires. Whoops. Then using wire ties, bundle the wires together and thereby keeping unlike wires separate. That doesn't make sense, does it? Fasten the wire bundles to the underside of the layout with stick-on wire fasteners. Or you can screw in eyelets and use wire ties. In areas where there's a lot of track, use many different colors of wire for drops and buses so you can figure out what's what. I use different colored pairs, like I'll use green and black, and I'll use red and black, and I'll use white and black. By color coding the wires, you can quickly tell which wires you need to test to find the problem in a given block. And document everything. Document, document, document. Make charts of what color wires go where. Make a drawing of the entire wiring layout. This is most important on bigger layouts, not so important on a little oval layout. And that's it. Larry, it's all yours.
Oh, okay. Does anybody have any questions for John?